okay. All right. So the participants have to accept it. So just for information, the speakers, if you want, you can. We want to put the video on the MIAI website, but if you don't want us to put the video on it, you just tell us, and we won't put it on the website. Okay. So that's it. We'll start with Aurélien Go. Tu préfères PPTX ou ouais, ok. C'est sur l'autre lien. Ouais. Ok. Je te le mets en plein écran. Et on est bon. Thanks. All right.
Okay. Welcome to this presentation on the paper DARTS. So it stands for Differentiable Architecture Search. So this 2019 paper was a revolution in the field of architecture search. So first, let's have a quick word on that. So as you may know, deep learning has enabled amazing progress in a lot of different fields. And a lot of this progress mainly relies on the fact that we were able to discover new architectures. However, these architectures were designed by hand, by human experts, and this is, it takes a lot of time. This is prone to errors, and we don't have any guarantee of optimality on these architectures. This is why neural architecture search has become of growing interest in the past years. In a neural architecture search, you have mainly 3 steps. The first one is to define a search space. The richer the search space is, the more it will take time, of course, to explore it, but also the richer the architecture you are able to discover in it, you can find. And you also have to define a search strategy. This is how you're going to explore your search space. And finally, how you can basically evaluate the performance of your architecture. So far, before this paper, the state of the art was relying on 2 main approaches in genetic algorithm and in deep reinforcement learning. So basically, we're using neural networks to find the architectures of other neural networks. And it was very, very time consuming, because each time you find an architecture, the way to evaluate the quality of the architecture was to train it from scratch. So it really cost literally hundreds to thousands of GPU days. Then comes this paper, Differentiable Architecture Search. So let's first look at the search space. So let's take very small neural networks. So here there's only 4 layers, and this small neural networks is called one cell, okay? And our aim is to find the best activation function, so between all of these layers. So you can see that for a layer xj, it's just like the linear combination of the activation of previous layers, right? And our objective is to find the best OIJ for each of these links. And we see that, okay, and we are giving ourselves also some candidate operation, O, which are all the operations we are allowed to use. So here, for example, some convolution, max pool, or ReLU. This has very classical activation function. And so we see that this is a discrete problem. And with the differentiable architecture approach, we are relaxing this problem to a continuous problem. So basically, what we're considering is that each connection is a superposition, of all the possible activation function. So when we look at this O bar ij, this is just the sum of all possible operations. And
just accept
yeah.
people. I don't know why. Okay.
So yeah, this is the sum of all possible operations, and these are weighted by some parameters that are called alpha. So you can basically make sense of alpha as the strength of the connection between layer I and j for a given operation, okay? So now, a neural network architecture is exactly equivalent to the vectors alpha. If we know alpha, this corresponds to a unique neural architectures. And what is really amazing with that view is that now our search space is continuous relative to alpha. So now, like, look at the difference with a training procedure that I will detail quickly in the next part. We'll see that some of the connection becomes stronger. And in the end, actually, we only keep the strongest one. So basically taking the Rmax over the operation between all of our layers. So this gives us our final cell, okay? And this cell actually is going to be repeated a few times to give us our big neural network. So let's now see how the optimization is done in darts, how we find this best alpha. So basically our goal is to find this alpha, and also we have to find the weights, right? Because to evaluate our architecture, we have also to train properly our networks to be able to evaluate it. So this is our optimization problem. If you look at the second line, you just recognize the classical way we train a neural network, just minimizing the loss train on like finding the best weights, W, of our neural networks to minimize the training loss. But we want to do that. This is a condition under which we want to find also the minimum on the architectural alpha. And actually, this is a hard problem to solve analytically, but the key idea of this paper is to make the following approximation. Instead of solving each time of training from scratch our neural network, we're going to approximate it with only one single gradient step. So what does it mean? This gives us a very, very simple algorithm. Because we have two parameters to optimize on, alpha and W, we are doing a double gradient descent, one step of gradient descent in the space of our neural networks, and one step of gradient descent in the space of our weights. And hopefully this will give us, in the end, if it converges, towards optimized architectures with optimized weights. So concerning the results, for example, I didn't. Okay, the camera.
I think the camera just.
Okay, can I check if it's on again?
I think if you're on the end of presentation.
Okay, I have to. Okay.
Non, c'est bon, c'est bon.
It's okay.
Le micro s'est remis par-dessus. Sur le truc.
Okay. And sorry for that. So if we test our algorithm on CIFAR10, which is a very classical image data set, here is the cell we obtained. Actually, we can see that the function that were found were separable convolution, skip connection, and dilated convolution. And if we look at the accuracy of our obtained networks on, for example, on ImageNet, we see that it obtains very comparable results compared to the other previous state-of-the-art method. But what is really amazing here is that it only costs 4 GPU days instead of hundreds or thousands of GPU days, which is a really incredible improvement. Thank you.
Thank you.
Yes. Okay. Type of question.
I have two questions. The first one is you said at the beginning that the old methods use the
reinforcement learning
genetic algorithms.
Yeah.
Are you talking about NEAT, for instance? Because it's a paper called NEAT, Neural Evolution of Augmented Topology, which was basically learning and architecture. And from what I recall from the paper, they were learning both the architecture, so the connections, and the weights, because basically the connection with zero weight was an absence of connection. So they were growing the network genetically. But it seems to me that they were learning both the architecture
do you know when this paper was released? Maybe it was before 2019, but because I know that.
Yeah, it was before. It was 2015, I think.
Okay. Oh no, okay, I didn't hear about this paper. And okay.
And
but,
the second question,
so it was pretty quick, right? Because it hasn't to train from scratch at each iteration, right?
Yeah, and you have a nice example of someone using reinforcement learning to train this architecture.
Okay.
And to be able to make an AI to solve a Mario level.
Okay.
It was able to compute all the commands for Mario to pass the first level. And
okay. But this was architecture search, right? Yeah.
Yeah.
Okay.
Yeah.
Okay.
And the second question is, okay, so the methods learns the weights between different possibilities of layers, but the macro architecture that you're talking about, so the macro architecture is still fixed, right?
Yeah, exactly. So this is like a direction of improvement. Is that like we are basically repeating the same cell, which is not optimized. So I've simplified a little bit. Actually, there's different kind of cells. They're learning classical cell and reduction cells, but still, you're right. This is a like fixed architecture, and the number of cells is also fixed.
Aside from the fact that the cells are copied, but even in the macro architecture that you draw, you have specific connections with
between the cell you're talking. Yeah, exactly. So yeah, if we would like to improve that, we would like to maybe design also a search space on how to put the cells together. But yeah, this is a direction of improvement that have been explored in more recent papers, I guess. Yeah.
And the cells are exactly the same?
Yeah. Okay. So exactly the same. As I say, there's two, or on the ImageNet, there were three kinds of cells, some classical cells and some reduction cells that just were basically convolutional cells. Okay. And they were learning two kinds of cells. Yeah, it's also chosen in advance. We see that it's not a very rich search space because, as you said, a lot of things are already imposed, but otherwise it's very, I guess, time consuming. And
it's not exactly clear to me why you have to optimize the network with two different gradient steps instead of like considering alpha as part of the weights of the net and making a gradient of the whole, like as if it was a bigger vector of a matrix of weights.
Yeah, why not doing one gradient descent and okay, considering?
Maybe it's just computational and more efficient.
Yeah, maybe it won't converge. I don't know. Yeah, we should try, but yeah, that's a good question.
We have time for one last question.
Okay.
Just a quick question. Do you know if they kind of enforce sparsity of the links? Because you can have all the links and they all have some complex operations that it's just too complex.
Yeah, actually, they also consider the zero connection among the operation, and sometimes some layers aren't linked by this zero connection.
Do you know if they can enforce sparsity by letting a lot of operations to be zero, or it's just it happens to be like this, but they are not doing anything with this.
I think with the zero operation, they let the network discover if it needs a zero operation. In practice, I don't know if there's a lot of zero operation, but here on the cell, we saw there was like all the operations were used, but yeah.
I think that from the way the formula that you explained at the beginning, it's a kind of a softmax.
Yeah, that's
so you will never have everything to zero.
No, but in the end, after the softmax, we are taking the argmax. We're only retaining only one operation. And so, some papers have improved it on taking maybe one or two operations with a threshold on the alpha. But in the end, we are not considering all the operation. And why we're dropping operation? Just because the GPU memory cost would be, of course, too high to like retain a network like that. Yeah.
Could we imagine adding a constraint that makes some way a light network? Like if I don't want my final network to be too big or too costly, can we add such a constraint?
Exactly, that has been done, and this has led to a very well-known architecture called efficient net, and this is actually the state of the art for like the past 3 years on a lot of different tests. And this is found with neural architecture search. Okay.
Okay, thank you very much. Thank you for your nice talk. Okay, there are lots of wires here, so you have to be careful not to disconnect anything. So Romain, are you okay for the next speaker? All right. So let me just change maybe one thing. People want to come. Can I?
Activer la salle d'attente, tu peux désactiver. Je sais pas ce qui se passe si tu désactives la salle d'attente. Si tu la désactives, je pense qu'il va être là.
Ouais, je pense que c'est moi.
Ou alors t'as acheté tout le monde.
Voilà, tous ceux qui étaient dans la salle d'attente, je sais pas. On verra. Ok, très bien. Hop. Et alors en plein écran.
Je crois que j'avais enlevé la vidéo.
D'accord.
La vidéo.
Ah, je pense qu'elle est encore active.
Non, elle est désactivée. Elle est désactivée.
Ah oui, pardon. Ok. Ok, donc là on a la vidéo. Ok.
Je peux l'accepter, mais.
Ah ouais, je regarde. Logitech. Ok, c'est bon, vous nous. And video is nice too. Ok. Ouais, ça c'était avant, ouais. Alors je sais pas si je peux mettre plus que ça en plein écran. C'est bon. Alors, après ça, je sais pas si ça marche, mais je suis pas sûr que ça marche. Attends. Je suis pas sûr.
Et on voit pas le
curseur. Ctrl-Shift-P. Mode lecture, ça va faire n'importe quoi ça.
Ouais, non. En fait, on y était déjà, je crois. Si tu reviens.
Ouais, j'arrive pas à...
Là, si tu fais flèche du bas, non? Que dalle. Ok.
Ah, attends. Ok, that was not. Anyway.
Ça va être un peu galère.
Ah, it's gonna be right. Okay, so just going back to the, so I have 5 minutes to convince you that interpretable AI for visual classification does exist nowadays, and that it's a viable option to more opaque ways to do visual classification. So explainable AI is different than interpretable AI. There's a lot of work on XAI, and interpretable AI is slightly different, and I'm going to try to explain you why. In explainable AI, you have a trained network, you have a pre-trained network, for instance, a classifier, an efficient net trained on ImageNet with a very high accuracy. But it's a black box in a sense, not that you don't have access to the weight of the network, because you do, but you don't, you're not able to put any semantic value to the inner layers and the neurons. You don't know exactly what the neurons are doing. So in explainable AI, the idea is to build a surrogate model, which is hopefully a simpler model and more understandable by a human being, in order to make an approximation of the black box. So you can do that either locally, so for a given instance, for a given image and a given decision, you're going to build a surrogate model which will be fairly accurate and represents the behavior of the model around this image. So that would be valid for this image and maybe slight differences, slight modification on the image, like rotations and shifts and stuff like that. So that would be a local explanation. So we do have algorithms to do that. For instance, the most common and most famous are line and anchors, and SHAP as well. And the optimal goal that you want to have is to have some kind of global explanation where you can explain very simply the behavior of the model for all possible inputs. But in that case, if you have a simple surrogate which approximates the behavior of the model for all the inputs, then why not use directly the surrogate model? So in practice, this is very hard, especially for image classification, because for image classification, if you take the pixels and you're trying to do a classifier using decision trees, it's never going to work. So that's the idea of explainable AI. But the problem that you can see here is that we are trying to you are trying to explain a model by building another model. So it's kind of shifting the problem to the surrogate model. In interpretable AI, the idea is we don't want a black box. We want to have something that will be able directly to compute its decision. For instance, in the case of a visual recognition task, the idea would be, okay, I give you an image and give me the type of the object. But to have some kind of reasoning process that is understandable by the human being directly. And so in recent years, one approach that has been very efficient for image classification is called case-based reasoning. Case-based reasoning is not necessarily linked specifically to image classification. It's more general. It's even used in legal term, because what you are trying to do is you are trying to treat a new instance of a problem by referencing to what you've learned before, to examples that you've seen before. And the idea of case-based reasoning is during the training phase. For instance, here you have what we call the fine-grained recognition task, where you have images which are very similar to each other, different species of birds, and you're trying to determine which species is the input image. So during the training phase, what you are trying to do is to extract prototypical representation of each class. And that means having, for instance, this might be the prototypical head for this kind of Aryan girl, the prototypical body and prototypical legs. And you're learning this during the training phase. And during the test phase, you take your test image and you compare it to all the prototypes. And you weight these similarities using, for instance, a decision tree. And at the end, you're able to say, okay, this is a human girl because this part of the test image looks like a prototype that I've seen during my training phase, and which corresponds to also a human girl. And as you see here, we have a model that is able to compute and explain its decision in a human understandable way. But that's the theory. In practice, things are a little bit more messy. So I'm going to skip the part where I show you a bunch of equations, because similarity in the visual space is very hard to define. So in practice, how do they compute this similarity between patches of image? They convert the image into their convolutional representation. So they use a pre-trained network, for instance, an efficient net or a ResNet, and they take the convolutional representation of the image, and they're trying to do some clustering inside the feature space during the training in order to extract this prototypical representation. And it's based on a very strong assumption that similarity in the visual space is more or less equivalent to a similarity between the vectors in the feature space. And the final decision is, so you have so the founding papers used a linear model, and a more recent approach used decision trees. The accuracy, as you can see, for instance, on the two reference data sets for fine-grained recognition. So this one is the bird species that I showed you earlier. And this one is trying to determine the model of the car. And as you can see, these two approaches, so using linear model or decision tree, give fairly good results on these data sets, but are kind of a little bit far in terms of AI. 5% is huge, right? But it's still good results, and they built a fully understandable and interpretable model, which is able to do fairly good on a very hard task, which is trying to determine different species of birds or car models. Okay, so the takeaway message is it's a viable methods to do image classification. you wouldn't use interpretable machine learning for all the possible tasks because let's face it, if it's just for recommendation for a product, you don't care about having something that is interpretable. But for critical application, that might be the key to having something where the user might trust the system a little bit more. And I think that's really important. And I'm convinced that, so the team which developed the first version of the case-based reasoning, so the leader of the team, Cynthia Redding, she just received $1 million for work on interpretable AI. So there's money and there's a lot of work to do still in interpretable AI. Thank you.
Thank you very much. Yeah, thanks for the presentation about the extraction of the similarity between the patches. So you use black box BI.
Yeah.
How do you ensure? So you have a step where you extract these patches.
Yes.
And then you make decisions based on patches. But how do you ensure that these patches represent something that is understandable to us, interpretable for us? So like that is, for example, a leg and the head of the bird, and it's not something that we cannot understand.
That's a very good question. And the thing is that I went a little bit fast on that, but actually when you put an image into a convolutional neural network, what you have is a map of vectors. It's like if you take a ResNet, it's a 7 by 7 by 2048. And in the original paper, and even in the second one that I was talking about, they are trying they don't know exactly where the important features are and in which vector. So they are basically trying to do a huge clustering algorithms with a lot of noise because they don't know exactly which features are relevant. But in the end, the loss function is optimized based on the accuracy of the classification. So the prototypes, the vectors that they are looking for inside this feature space naturally converge towards something that is meaningful in practice. But I agree that the main problem here is that is to find what vectors in the feature space are relevant for the object. And so one of the objectives of my PhD, and I'm working on it right now, is to do some kind of semantic segmentation before doing the learning of the prototypes, trying to determine, okay, based on this map of 7 by 7 or 8 by 8, which are the vectors which are relevant for the object.
So like the whole procedure, it seems to me that it's based on the assumption that what are the meaningful pieces for us to take a decision are the meaningful pieces that will be retrieved by the net, so that you cannot take that decision by choosing very far away meaningful pieces for decision to be taken.
Yes and no. In practice, you see them converge towards something that is meaningful to the human being. But if it's not converging towards something that is meaningful to the human being, but still really relevant to the classification, then it means that you have successfully identified a bias in your data. For instance, there's this example of a train classifier which was very good at distinguishing between wolves and huskies. And when they actually applied Lime to the model explanation, they found out that the model was actually looking at the snow rather than looking at the husky. But it might be a way to identify bias.
Thank you.
Okay, other questions?
Yes.
What's about the training time of the models comparing to the state of
It's comparable. It's comparable. It's a few days on the GPU.
How can you like the clustering in the feature space? How do you do it exactly?
So they turn it into an optimization problem with using the backprop, where they are trying to minimize the distance to the closest prototype belonging to the class and pushing away the closest prototype belonging to all the other classes.
Okay, so first, okay.
But they do the computation at the L2 distance in the feature space as something that is that will be used by the gradient descent.
The prototype of the class is the average of all the image in the feature space.
Yes, and so they do the clustering, and then they will take the closest points in the feature space to the centroid of the clustering, belonging to something in the training set. Because you're not sure that your centroid is going to actually belong to the training set. So they take the closest one.
One last question. I'm not a specialist of attention models, but it seems to me that it might be a tool to tell you whether to look at the image and directly, maybe, how should I put this? If you want to know where is the information relevant, well, use this kind of model to say, okay, so the head of the bird can help me, or the body can help me, or whatever. I mean, is this kind of model useful for that?
I think it's the other way around, because when you're trying to decide which features are relevant for, it's with respect to a given model. So you have a trained model, and then after that, you're scratching your head and saying, okay, where are you looking? Where are you looking at? And so there are a bunch of methods which are post-hoc explanations. So meaning you have the trained network, and then you make a decision, and you compute saliency maps, which are going to highlight the regions with the highest gradient with respect to the decision. So you can do that also with the black box model, as long as you have the weights.
Yeah. Okay.
But for a bad decision, for instance, a black box model looking at saying that a bird is I don't know, a car, and saying I was looking there to say that it's a car. It's still a bad decision, and you know that it's looking there, but it doesn't give you any kind of information.
Okay. Thank you. Thank you very much. So our next speaker, I call Laura. Yeah. you're there. Sorry?
The planning I was supposed to be at the end. No?
You were supposed to be at the end?
Yes. It's the order of the presentation.
Oh, no, I just did it randomly.
So
you still need a bit of time. It's all right. I can go.
just
Surprise.
If you like, I can leave you.
No, it's okay.
Okay.
I didn't expect to be phoned. I have this.
Okay. Oui, du coup, celui-là, c'est OK? Tu sais, celui-là,
juste pour le compte.
Attends, non, c'est trop cool.
Ouais.
On va mettre la caméra ici. Ah, effectivement, c'est bien, ils m'ont pas donné. Enfin, je pense que ça fait pas pour ça. Ouais. Ouais, c'est ça, il n'y a pas de... Okay, so Flora Gottmonster.
Okay, so hello everyone. I am Flora Gottmonster, and I will talk about a paper which presents a conceptual and computational model of smart decision making in human and artificial agents. So as you already know, models of human cognition are very efficient in limited environments, such as games, which are like very specific domains, but they are struggling in the real world, which is much more complex and dynamically evolving. This is particularly challenging when there is in the domain of morality. But the fact is that to bring morality into artificial agents is very important, because some artificial agents can be in contact with human beings and cooperate with them. So the model I will present is named LIDA. It was built upon findings in cognitive sciences and neurosciences. So how does it work? So the agent is perceiving the environment, and have sensory information. Then those low-level features are converted into high-level features, such as objects, categories, actions, feelings, and so on. So, for example, the idea of forest or leaf. Then those precepts are set in a workspace. So this corresponds to the situational model of the agent. So what the agent understands about the world. Those precepts are then used as cues in episodic and declarative memories. So for example, the idea of a forest can bring the idea of wild animals. And those local associations are associated also with percepts and are building into structures which make sense to the agent. So then those structures, like global ideas, are going through a selection attention process, so which leads to select like the more important structure, which is then sent to a global workspace, so to the consciousness of the agent. Then, so this is the idea, like what the person wants to do. For example, if the person wants to escape from the forest. And then the procedural memory corresponds to all the possible results of the different sections. Then with those information, the agent is able to select an action and then to traduce this into a behavior which impacts the environment. And then there is this cycle of the model. So this is like a very general and comprehensive model of cognition. And now how does morality intervene into this model? So for moral decision making, two things are very important, which are like emotions, moral related emotions, such as pride, guilt or shame, and also the fact that there are some moral rules that intervene into the decision making process. So, for example, if an agent wants to decide where to copy a computer software or not, the information will elicit some moral rules which will be associated with emotions. So for example, like you should not steal. And those structures will be like a dialogue. And with some structures will be in favor of the idea, and other elements which will be like objecting this, and this dialogue will evolve until there is no more objection to the dialogue. So the final ideas will lead to the selection attention procedure. So this model is like very complex and difficult to implement, but its main advantage is that it's a very comprehensive and general model of cognitive intelligence. It does not put the moral domain, moral decision making, into a specific and modular thing, like apart from the general intelligence. And also it helps to model both affective and rational features of moral decision making, which is like very important to better understand and have insights about the moral decision making process.
Has this already been implemented in something, or at least partially?
Okay, so the NIDA model was already implemented like for different domains, but not with the moral like specification. It's just like a conceptual model, but yeah, it's really hard to implement because it's like a very complex model, but yeah, it helps to give like a very big insights about how moral decision making is part of our intelligence. Now we could be like set into models of this moral decision making.
Moral rules have to be given to software?
So yes, actually, the agent is also learning during the cycles. So for example, when an action is made, the agent can see the results of the environment and learn. For example, if there is like a bad result from an action which leads to emotions, so the agents can learn moral rules like you should not do that. Also, it can learn like from its own experience.
Thanks for the presentation. Yeah, I was wondering if this is a theoretical model that researchers build based on their knowledge on decision-making systems and cognitive systems, or also they try to do some experiments for some practical cases with this model, and this model helps. So if you could give some examples, if this is the case.
Okay, so it was used for the army, if I remember well, but only the LIDA model, not with the moral implementation. Yeah. Yeah, it was like to organize, how do you say, organize planning and like organize things like, I don't know, like precisely.
And so the agent in this case, for example, the case of the army, what was this agent? What was, for example, its perceptual memory or its transit episodic memory? What was how was this agent built? What was more or less
okay, I'm sorry because I mostly know the implementation of LIDA in the particular case of like moral decision making, but I don't know exactly, like it's like a different topic, but it's, yeah, it was to organize the planning of persons and how to manage the planning of people, which are like, yeah.
And just last question. What is the conscious broadcast? I didn't understand exactly.
So this model also aims at explaining the consciousness phenomenon. So how that some information come to the conscious of the agents. So yeah, the workspace is like the working memory, and it's like processing information. And once information is selected, it's sent to the conscious part. So it explains like why we have so much information, like perceiving so much information, but being conscious only of part of them. But yeah, it's like not really useful for the case of morality, just like because it wants to explain the consciousness.
Yeah. So it looks like all these model decisions before taking the action. Looking at this model, it looks like they are unconscious. I mean, we make them before being conscious of them.
Yeah.
Is it what I right? Was that what I understand?
No, it can be both conscious or unconscious, and it's like also explaining why some actions and decisions are like made, how to say, intuitively, or other like rationally with some reflection. So it depends where the information is like is set in the cycle, because you have this cycle of information, which is like yeah, I don't know how to explain where, but depending on where the information is processed, it indicates whether it's conscious or not, but both are possible.
So it concerns moral rules. So when you implement this kind of architecture, does this mean that you have to find an encoding for defining for the moral rules? And so do you have to because you said that the agent is learning constantly. So are the moral rules something that is hard coded by a developer, or something that is an abstract representation of the moral rules that was learned through examples?
I think both are possible. It's like if you think about the conceptual model, you can think about a very complex implementation with the agent which will learn from the beginning, so which will learn different states of moral development and so on. So it will learn by itself. But I think the fastest way to implement this is to already set the moral rules in the model.
And so if you set the moral rules, then it basically depends on the culture of the developer or the environment and the society the developer is. Yeah. So you could have the same agent with different moral rules depending on for instance, the country where it's.
Yeah, it's really complex because you have moral rules some moral rules that are conventions of the society, and some moral rules that are more personal. But you accept those moral rules also depending on your personality and on your personal experience. So because you have those moral rules into memory, it does not mean that you will always act according to those moral rules. So it will be the association process that will differ between individuals.
Okay, but you could possibly have thousands of agents with each of their own variations of moral rules.
I think it will be the same moral rules for everyone, but different access of those moral rules and different use of those moral rules depending on of each agent.
Thank you.
Okay, thank you for your questions. Thank you, very interesting. Now it's Mathilde. Okay. So thank you very much for the so that's it. All right.
Hi everyone, I'm Mathilde. I started my PhD in October here at the League, and I'm supervised by Denis Tristam, who's directed MIAI team Edge Intelligence. And so I'm interested in the environmental impact of AI, and yeah, the subject of my thesis is more about developing low-cost models. And so for a few months, I've been working on how we can estimate the energy consumption of training an AI. And doing that is because the part of digital activities in the global energy consumption is growing approximately 6% by year. And we're trying to better understand what the part of AI in this, and if the first step towards doing that is actually measure it. And so today I will present tools that allow you to do that. And what I want you to say is that, yes, so the main message for me today is to show you that it's easy to do that, and that, maybe my more important message is to please report it so that we can, better understand the impact of AI. And so how can we do that? I have found that there are three main ways to measure the energy consumption. The first one is to have a very simple estimation based on the thermal design power, which is more or less like the power used at the maximal usage of your processors. So then you just multiply by the runtime, and you have a first estimation of the energy consumption. And there are tools, online tools to do that. So this is a website, Green Algorithm. And so you can see that you can fill the runtime, the type of core of your CPU and GPUs, and a lot of other details. And it will provide you with the carbon footprint, energy, and the other metrics. So it's very easy to use. Second way to do that is to have actual measures, so use wattmeters, which has the advantage of not being an estimation, so you have a real value, but you will not have details per CPU, GPU, so yeah, it's the whole machine. You don't have a lot of details. And finally, you have software power models that were that it was shown that the estimation were better than the first one I talked about. And they are based on hardware performance counters, which are like, I think there are like more than 400 counters. So it's more complex, and I won't be able to explain that in 5 minutes. And there are a lot of technologies based on that. The first category is Python packages. So you can see that the most I've found are very easy to use. So you import it, initialize it, and then you start and stop the tracker around your training. So very simple to use, and it will give you better estimation than the websites. And finally, you have what I call profiling software that allow you to monitor your CPU and GPUs. And they're also quite easy to use. And they will give you way more details than the Python packages. But that's not that simple. You need to take into account external factors. So the most famous one is PUE in the context of data centers. So that's a metric, power usage effectiveness, that allows you to take into account the cooling in data centers. And the less common factor is the pragmatic scaling factor that takes into account that you're going to train your model more than once before you actually use it. So, yeah. And finally, some tools will give you carbon emissions. I just wanted to explain to you how we get to this value. So we only multiply the energy by carbon intensity, which is expressed in gram of CO2 equivalent per kilowatt hour. And this value is actually can be very different depending on where you live, when you take the value, and there are also a lot of sources. So this is electricity map that will give you real-time value and per country, but you have also a lot of sources, and you'll see that it results in very different values in the end. So yeah, I'm not going to spend a lot of time on this. Let's say that I trained a very simple model on a Grid 5000 platform, which has wattmeters, and let's get to the point. So I've selected two websites that make a simple estimation. The wattmeters, and finally, Code Carbon Experiment Impact Tracker and Carbon Tracker are all Python packages. And finally, Energy Scope is a software that computes energy values. I don't know how much time I have, but this is my results. So on the left, you have the energy as given by the tools. You can see that the values are very different, but it's actually mainly due to the fact, partly due to the fact that they use different parameters, as for example, PUE can be very different. So what I did is I normalized the values so that as if they were all using the same PUE. And there are still quite some differences. And what you can say in the end is that Green Algorithm and MLCO2 impact are like the most simple estimation that give you a value very different from the wattmeters, but they're very easy to do, and you can do them like before or after the training, so it's very easy, yeah. And finally, Energy Scope, I would say, gives the best estimation, but it's hard to say, and maybe harder to use than the 3 Python packages. that give you different values, but are also very easy to use from my part. About the carbon emission, because the value are even more different, and that's due to like the carbon intensity value chosen. You can see that some use a very big value, which I think is the world average. And then you have tools that are able to retrieve the local values. So for France, we have a very low carbon intensity. So yeah, so maybe I'm not going to talk about this. So in the end, you have various tools that allow you to do estimation of the energy consumption of training your AI. So maybe the message is to provide it when you can. And of course, the limits of those tools is that they don't take into account the like the fabrication and the extraction of materials and the processes, and also it doesn't take into account the usage of the model, so the inference cost. And I guess I have reached my 5 minutes. So no problem. Thank you for listening.
Thank you very much. For questions. Let's start those who didn't ask.
Okay.
It's not directly related, but I suppose that coding in Python is like consumes 70 to more times more energy than coding in C.
Yeah.
So like a lot of machine learning libraries are in Python. Do you think there is an impact, or because they just code something which is coded in C, so in the end it's not there?
Are there some like AI models written in C? I guess it's. I think there are some compilers that allow you to save energy. But I'm really not an expert on this.
Yeah, but the low-level functions in TensorFlow or PyTorch are compiled. I think they're compiled in C Python.
Yeah, so I'm wondering if the 72 times is also applies to the case of machine learning.
I hope that. So in the increase in the power consumption by multimedia applications, and what is the part of AI versus the part of blockchain?
Very good question. I don't know.
Because we might be trying to optimize something where the AI consumes, I don't know, 1,000 times less than blockchain.
Yeah, I guess you can make improvements everywhere.
Yeah,
So,
yeah.
But I don't know, sorry.
Also, yeah, about the same curve, I was wondering, since it's a share of the global energy consumption, how much does it take into account the fact that technology might be reducing the total of the energy consumption? So it's increasing the share, but maybe also because the total energy consumption is decreasing, and might be also thanks to technology.
I can give you references. Actually, I don't know. It's a very good question. I started my PhD 4 months ago.
Might be important. Like if it's, I don't know, we're strongly reducing total energy consumption thanks to technology.
Yeah. And I don't know. We are electrifying everything, so of course the energy consumption is going to increase, right?
Well, why do you think so clearly that not? Because like it looks to me that we're going towards like a service-based society, which in general is less implies less material usage.
You actually need more materials. You need metals. Rare metals.
And there are other issues like I think, I mean, I don't have a lot of time to speak about it, but like the cost of fabrication is bigger than the use of your processors. Like even if you use your CPUs for 10 years, it would not cost as much as how much it costs to make it. I mean, as numbers are not probably not right, but like for your smartphones, the cost is already bigger than the time of use you use it. Does that make sense?
Yeah.
And we don't know, how much material we have left in the earth. So. And I
mean, can we just really talk like this, or maybe we don't have the time now?
2 minutes left. Let's say 2 minutes left, and
we're good.
I
just wanted to maybe show you quickly. I don't know if I had the time before, but like all the tools that I've shown, they give advice on how you can reduce your impact. And there are some things that are used to like select the data center that has the best PUE, or be careful of when you train your algorithm so that the intensity is the lowest. And maybe like do random search instead of reach search when you train your models. Just pretend that was, of course. And adapt your algorithm to the hardware, but that's all to do if you're not an expert in CPUs and GPUs. But just an example.
Okay. More practical questions.
30 seconds.
What is the tool that you suggest, because I didn't.
So here's a list. I think for me the most easier to use is Urban Tracker. The Python packages for me are the easiest to use. And energy packages are very good because you have the real-time evaluation of the power. So, and for me, it's really nice because you can see which part of the training is taking the most power. So that's more interesting. It doesn't only give you one value in the end.
Are they AI based?
AI based?
Are they based on AI?
No. No. I haven't. I didn't give much. But I can give you the full presentation.
Yeah, all the presentation will be available on the MIAI website.
I told you that first, but I made this presentation at MIAI meeting last week, so I have like 20 slides.
Okay, so it's quite longer.
I cut the half.
Okay, thank you very much, Mathieu. Yes. Okay, so my turn. We'll finish a bit late. I think they won't punish us for that. So. It's already open. Yes. All right. Okay. Right, everyone. So, hello everyone. I'm Luca Etono. I have 5 minutes or maybe a bit more to present you a way to estimate Gaussian parameters and a way to impute missing values in the case where the data that are missing not at random. So I'll get a bit into more details about what that means. So we'll first define the problem that we want to solve. It's really like a homework you would do in master. So first, we consider a data set X that follows a normal distribution, okay, a multivariate normal distribution. And we set our case in a high dimensional setting, which means that we have less samples to analyze than covariates that there are in the sample, in the data set. So we suppose that each sample are independent from each other, and there are missing values in this data set. So each sample is composed of an observed part and a missing part. We also define the matrix that we will call the missingness indicator, which means that it's a matrix of size, same size as the data set, and that tells you if the entry xij is observed or missing. 0 for observed and 1 for missing, let's say. So the problem is here with this missing data, can we estimate mu and sigma? And other question, can we estimate the missing values? Okay. So to do that, well, like a homework you would do in master statistics, well, you could write the likelihood of the observed variable and the missingness indicator. And we will try to maximize this likelihood with respect to the mu, the mean, and sigma, the covariance matrix of the data. Okay, so we'll denote another parameter, which is gamma, which will represent the parameters of the distribution of M. So typically, gamma could be, I think they don't see me here. Typically, gamma could be the probability of a Bernoulli distribution. Imagine I just flip a coin, and every time the coin is on tails, I mask the data. So this is a way to generate missing value. Okay, so this is what represents this gamma. And the likelihood, we could write it the following way. Well, using Bayes' theorem, we can just simply decompose it into the likelihood, the simple likelihood of the observed values here, and the likelihood of missingness indicator with respect to observed values. So the likelihood of observed values is really easy to compute. It's simply the normal distribution. It follows a normal distribution, so we simply take the probability density function of a multivariate normal. And for the second term, well, we don't really know. It depends on situations, as we'll see. Okay, so according to Rubin, a statistician from last century, he classified missingness mechanisms into 3 types. The first type is that it's saying that observations are missing completely at random. So this typically corresponds to the flipping coin mechanism. Okay, so it means that the probability, the distribution of missingness indicator does not depend on the observed or unobserved values. Okay, the second missingness mechanism will be said missing at random, which means that the missingness distribution only depends on the observed values. And finally, all the other cases will be referred as missing not at random observations. Mainly, it means that the missingness mechanisms will in some way depend on values of unobserved variables, on missing data itself. Okay. So in the case when the data is MCR, is missing completely at random or missing at random, we have a nice property, which is that this value here does not depend on parameters mu and sigma. So if you want to maximize the likelihood, you simply have to maximize according, simply have to maximize this term. Okay, so this means that we simply have to maximize the likelihood of a multivariate normal, which is quite easy. Everyone knows how to do that. And or you can use any software that will do it. So hooray, we have our solution. Now we are interested in the case where we have missing not at random data. So in the case we have missing not at random data, this problem becomes much more complicated because this thing will depend on mu and sigma, and we don't have a clear expression of that. So to solve this problem, we have to specify a missingness mechanism, which will be referred as P of M, knowing the whole set of values, X, okay? And we need to specify this missingness mechanism if you want in some way compute this thing and maximize it then to according to sigma and mu. So to do so, there is a paper that came out 5 years ago, which is, the name is here, Penalized Em Algorithm incorporating missing data. So the short name will be PEMM for Penalized Em Algorithm for missing values. And so the aim of this algorithm is to maximize the joint likelihood that I present you with respect to mu, sigma, and the missingness parameter, and in an MNIR setting, and also in a high dimensional setting, which means where you have less observation than the number of covariates. So more formally, what we want to solve is the following thing. So we want to maximize the log likelihood, but here we add a penalization referred here as P of sigma. So we add a penalization term on sigma matrix. Why? Because in a high dimensional case, the natural estimator of sigma is non-invertible, and we want it to be invertible if you want to compute a likelihood. So we need to add this penalization term. This is what they propose. I won't get much into details of what is behind this penalization term, but you may ask it after. So the penalty term enables estimating sigma in high-dimensional setting, and they also specify a missingness mechanism, as I showed you earlier. So they decided, for some reason, to specify this missingness indicator. So as you can see, the probability for an entry to be missing is actually depends on the missing value itself. Okay, so this is what I say about missingness indicator that depends on the value missing itself. Okay, so the aim here is to maximize this penalized likelihood, and to do so, we'll use a EM algorithm, or what we'll call a penalized version of EM algorithm, where we first obtain the initial estimates of sigma, mu, and gamma, and at each step, the aim will be to, instead of compute this log likelihood, we'll compute the log likelihood of joint distribution of observed and missing values. So we'll compute the log likelihood of the whole data set, and we'll take the expectation of it over the missing values. Okay. So they managed to find a way to compute this stuff, and then at M step, you simply maximize this expectation with regards to the model parameters, so mu, sigma, and gamma. And you maximize it, taking into account the penalty term here. So you respect that the constraint of the likelihood you want to maximize. And so a result that you have is that maximizing this quantity at each iteration makes that necessarily we will increase this quantity at each iteration. So this is one of the main advantage of EM algorithm. We are sure to increase the objective likelihood at each loop. So now you're going to tell me what about the second question, which was about estimating the missing values. Well, again, in this algorithm, we have a nice property, which is that at each step, when we compute the expectation, well, it means that actually at some point, right, when we compute this, we'll compute the expected value of the expected values of missing values. And so this will serve as a natural imputation way in our algorithm. And so at some point at the end, we will have found the estimators of the parameters, and we will take the last values of the expectation of missing values as imputed values. So this algorithm enables to solve both problems, and one of the application in which I'm interested and for which the algorithm was developed for was mass spectrometry-based proteomics. So very shortly, it's a field of biology that wants to quantify and find and quantify a set of thousands of proteins inside a biological sample. And for that, we use like mass spectrometer, which is a very big instrument with a lot of variability. And the problem is that the detection threshold of the mass spectrometer is not fixed. And so low abundant proteins are less likely to be detected by the measure instrument, by the mass spectrometer. And so we have to establish a MIAI devoted imputation algorithm of imputation. Okay, so I'm done for it. Thank you. Okay.
I have two questions. The first one is, so from what I understand, you're trying to jointly learn the parameters of the Gaussian distribution and the distribution of the missing values.
Exactly. Exactly.
How are you sure that there exists only a single stable value for this?
We are not. This is a property of the EM so it shows you. So the EM only ensures you that you will increase this quantity at each step but you will probably get into a local maxima.
Yeah, it's like gradient descent when you end in somewhere where the gradient is 0, you don't know if you are.
Exactly. In this case, we don't know. Depending on the missingness mechanism you choose. So with this one, there might be some other missingness mechanism that makes your problem concave, and so you have a unique solution, but it's quite hard to verify. So yeah, as you said, we only sure to go to a local maximum, but we don't know if it's a global maximum.
So here the value gamma 0, gamma 1, they do depend on sigma and
No. We suppose
so they are decorrelated from the parameters of the Gaussian distribution.
Exactly. They are. We suppose they are completely separate parameters for it. It's an assumption. It doesn't necessarily have to be like that. Okay. Yeah.
Differently as to, do you want to ask it that estimator is kind of consistent in the sense that if we have this is generated by this ground truth parameter, and if we have the number of data tend to infinite, that if whether using this maximum likelihood estimator gives us the true parameter.
You mean how far are we from the real parameter by maximizing this likelihood?
Or can we, like in the infinite data region, can we get the true parameter?
Okay, so to answer the question, I should compute the bias of my estimator and the error quadratic mean from what I remember. To be honest, I haven't computed the bias. Okay. I don't know, because as I said, we only show, I think it's very hard to compute the bias of an estimator resulting from EM algorithm, because you only show you go to a local maxima.
It's related to the algorithm.
Sorry?
It's not related to the algorithm, but it's only related to the estimator.
Well, the estimator is computed with EM algorithm, so the estimator depends on your.
Maybe the problem is not well formulated. So I'm talking about the maximum likelihood estimator.
Yeah.
So EM is a way to get this estimator. But suppose that we are given this estimator like by some magic, then is this estimator consistent?
If you take a Gaussian distribution in n-dimensional space,
yeah,
and you have a ground truth, you specify the model of the missing values,
yeah,
you generate these data sets where you apply your missing algorithm to remove values from the data sets, and you apply PM. Do you end up with the correct parameters for the Gaussian distribution and the model for the missing values? Was that your?
I'm not sure.
You generate your own ground truth, and you apply the algorithm, and you try to find.
I don't apply my algorithm, but I just use the ML.
MLE is your answer. Your question is MLE without bias? MLE estimator without bias?
So I think
maximum likelihood.
In general, I think.
So here we're seeking for the maximum likelihood estimator, and you want to know if it's without bias or not, or with bias.
No, it's not. Whether this is consistent. It's better than the problem that he asked. But there are two problems. One is with the statistic problem, that whether the MLE estimator is good, and now maybe it's always good, I'm not sure. And the other problem is related to EM, I think also depends on. Maybe we can.
Yeah, maybe we can have a talk after. So I'm not entirely sure to get everything you Is there any other questions?
And how does it scale if you don't take a Gaussian distribution, for instance, a normal distribution, for instance, but with more moments, a skewed normal distribution, for instance, is it possible to expand the algorithm to take more moments into account?
Well, I haven't tried. So the thing is that in the end, they have analytic exact formulas for the maximum of the EM step. And if you don't consider a Gaussian, then the estimation of the maximum will be much more complicated. So you'll need some sort of gradient descent, I guess. to find the maximum at the end step at each iteration. So I think in theory, yes, but I haven't tested for any other kind of skew distribution, which is actually more realistic in the case of proteomics, but we have to do approximations. Okay. All right, so I think it's time for lunch. Sorry for those who are not there. I hope, I don't know if they had any question. No? No, okay. All right, so thank you everyone, and see you next time. We'll try to set this on a regular basis. So I hope this will continue for the next month, maybe 2 or 3 months separate between each presentation. That would be cool. And see you. See you. Bye. Okay. Au revoir.